So Hello r2con, this is Edic Freaks JP. Would like to make a presentation about the cell code part 1. It's a basic one. This talk is all about first we start with the introductions, and then we will talk about how the cell code works with the methods and the concepts, cell code and its analysis methods, analysis technique in radar, and the concept to defending our boxes with following from the forensic perspective, and IR handling management, closing by the appendix explanations. Well, about me is the same, just another security guy. This is another give back and still doing the same stuff. Introducing about this talk and its sequels. I've planned about the series of talk actually starting from 2018, and this is actually the for this year's talk, focusing to the cell code part 1 in this r2con, and the second part for the advanced one in the r2con. So what this talk is all about is for the blue team or basis sharebacks, and this meant for the non-operational talks for explaining about the basic methods, and then it's strictly about our own research. The background is the cell code is a sequence of the bytes that represents assembly instructions. That's it, with many counter purpose that and the characteristic that explains here. There's so many of them, but in the most important one is what and why and how we have to analyze the cell codes. There are so many cell codes, and then its source code is shared in the many repository everywhere in the internet, and the post-exploitation tools are using them, and it's aiming OS and platform architecture from the endpoint servers at the mainframes can affect your OS browser and applications. The cell code checklist goes like this. The purpose is to gain cell as a loader, downloader, further intrusions. Sockets are used a lot to be fileless, and how to collect cell codes following the post-exploitation tools, self-generated adversaries intelligence, and how to troll them in the internet. Supporting the knowledge for the cell code analysis, you have to know about the Cs and the operating systems, the uses of the randomized stacks and stack protections. You have to know how to use compiler, linker, disassembly to produce and build yourself to understand it better, and so on. Then what we are trying to do now is how to understand the analysis for the cell code. First, you have to know how the cell code is built. Define what operation that you will be performed, code it to the R2 assembly, and then you compile it, grab the opcodes, and then you put in the wrapper and compile it again and ready to use. This is the wrapper that I'm always using for the analysis in the cell codes. And yes, first is put the code over there. So I name it the cell code, and then we think about what kind of the operations that we want to put into that code. In this case, I make some simple 30-bit assembly for the executing the exit 1 and exit through the syscall 1. So first is clearing the EX, and then move the AL to bits 1, and then invoking the system call in the interrupt, and done. All we have to do is compiling this to the with the N assemble, and then try to link it with the LD. Oops, I missed the -O, but it's supposed to be it's supposed to be compiled anyway. It's supposed to be linked anyway. So let's see. Yes, it runs. Okay, let's make sure whether the binary is there. Call it to exit. Okay, it is there. This is cell code actually. Rather go to the right into the EEP to the entry 0, and these are actually the opcodes that parse from the rotary opcodes before. All we have to do is form it to the form of the strings, and then like this with the escape strings, and all we have to do next is copy paste these strings to the template of the wrapper that we made before, like this. Copying, go back there, well, put it the strings over there, and then it will it will check the length and print out the length, and then going to execute the shell code afterwards. Okay, looks good. So all we have to do now is we have to compile, but beforehand we make sure that the randomize VA space is disabled to make it run, and compile it. Compile it is to understand it without using the stack protectors, and make sure that it can be executed in the stack like this. Oops, there are some warning. No, it doesn't matter. This is warning. It looks good. So it's supposed to be compiled. So this is the oops, missed the one, pin one. Yes, that is it. It is running. So all we have to do is seeing the result in the radar array. Okay, oops, missed the one again. There you go. Then go to the visual mode. Okay, we don't know where the shell code in this kind of the blobs, right? So we go back to the what we pasted before, and we pick that up codes again, and we go back to radar interface and search it with /x, going to that opcodes, making beautified like this, and then you will see the hits. Mark it and going there, then go to the visual mode again to make sure that okay, this is the shell codes there. It is actually being marked with strings of the imported. It's supposed to be so. Let's go to the main function. It's supposed to be there because the symbol is there. Okay, this is the main, and then yes, actually it is detected as an object shell codes. So as you can see, it's using the std out and seeing the length, and then to print out. Okay, this is the shell code itself. It's beautifully written. There you go. And let's make sure whether it runs or not. Let's trace it. Okay, execute it. Okay, it's exit with a status 0 in the end. First is checking the memory allocations. Write it the length and measuring the length first. And this is how it goes. So this is actually how the shell code is made. Now it's about setting the environment. Environment for the operating system for the Linux is quite easy. You have to understand about the syscall, but for the Windows system is quite delicate. You have to understand about the API. So for the this API stuff in the Windows, I'm gonna make some demonstration for it. There is a good tool called rwin, and this rwin tool is actually open source and made by the Mr. Steve Hanna, and thank you very much for his good work. And this is the code. It's pretty simple, and all you have to do is compile this code. I'm using the code blocks for this purpose. Yes, like that is supposed to be built. Yep, there is a rwin.exe there. Okay, there is an exe file of the rwin. There's headers, mz is there. Okay, so it is supposed to be executable. Now, how to use it is just aim the library and the function call afterwards, and it will just like that, get processed just like that. It will show you the actually address of a certain calls in the memory. The other tool is a dump-bin. Dump-bin can dump many parts of the binaries from the export, relocations, import, etc. like this. Yep. There is many options for it. You can use it, for example, for the kernel 32 in the Windows. It will show the RV address. It will show also about the hint address and ordinal address as per explained it in here. This address is very important if you want to see and know about the shell codes, but you have to know also exactly how it is imported address that can be used for the further shell coding. The radar array is in Windows is a very useful purpose. Okay, the analysis concept, static analysis of the shell code is dissecting the shell code without executing it. So it helps, the good binary tools will help you much for the understanding its readings and to understand about how it works, and to guide you many stuff, can emulate to help you analyzing it, and rather is very good tools for it. Challenges obfuscation, packing, and encryption. The analyzing concept for dynamic analysis is as same as dynamic malicious binaries analysis, and you have to execute it with debugging or tracing them. And the challenges for this is anti-debugging, VM detection, checking the real-time environment. Okay, so we are now starting to go with the analysis in the route array. Remember, do the stuff that you're good at. So here we go. R2 practical cell code static analysis is recognizing the wrapper, using the payload, seeking them, dealing with adjustment with cache, and dynamic is constructing the executable on memory analysis, and then recognizing the payload, and then the emulation analysis is for using the ESIL and some woo-woo from that is very interesting one. For Windows and Linux cell code analysis on Rudder, there are some points that I need you to understand beforehand. In Linux, this interfacing with the kernel is very important. You're dealing with a system call. In Windows, there are many stuff that you have to concern, like as per written there. The challenges is for Windows and Linux are written in there also. So let's go to. Okay, we're gonna do some demonstrations, but the analysis of the static. I'm using firstly the simple cell code analysis that is written in the Rudder book. It is these cell codes. So we are using the same wrapper as I used before, and as per instructed in the book. So let's try to compile it first, simple, without doing anything. So make sure that all of the symbol is there to make the things a little bit easier for us to analyze this. Then now we start to fire the Rudder array to these binaries, and let's perform the basic analysis. Otherwise, you cannot see the AFL result here. There is a function main. We go there and then try to analyze it first, and then we see there's an object of the cell code over there in that address. So we just jump to that address and try to print it up. And we'll see two strings here, which is a very bothering. This is actually a NOP code. It's really making the reading quite difficult. So I had to ask the pancake about how to get rid of these strings reading. So I got the advice about us using these two commands, and we can try to printing out again. Well, okay, we try to print about the 60s in length, but it looks like the cell code is a little bit longer, isn't it? So just trying to count the cell code, make sure the beginning and the ending is correct. But we are, yeah, that is a whole like 27, 28, yeah. Then okay, first is going jump to this address from the top, and then go back to the second lines with popping the RSI. Then after it being popped, the return address of the RSI. It is a mismatch about the ESI there, so it will be set to the next line. So then we are cleaning up the value of the ECX and moving the 27 to as a counter there to the lower bits, and we have the 35 to be put as a subtraction values, and then we have the another subtractions for the looping, I presume, with a value of 1. So this is actually about what it does. Dealing with this in Rudder array, well, we can simulate this operation with a WO command. But beforehand, we have to use this protection first to make sure that the binary is not being rewritten. So with the IOCast, we can activate it, and we just do the WO command. And the WOS is for the subtraction we are using for this purpose. We are subtracting the 35 hex first, and then to the address next to the ESI, and with adding the counter loops. It seems right, so let's see. about the new PD here. So we will see the two, syscall was appearing there. Now it's making much sense of this binary. The first is 0xf is an exit syscall, and 1 is for the chmod. Chmod 1 is a weird. There is parameters for it, and 1ff is we can ask the router about that and see the octal value is a 777 and chmod 777 for what. We'll see the next arguments by dumping this rest of the binary, and we'll see the etc password is there. This is a very not good kind of the shell code. Okay, so let's go to the dynamic analysis. We have this talk in the Luxembourg before. There is an injected processes, and then we have to analyze all of the aspects over there, from the memories, from the processes, and from the list of files also to confirm the socket. Then we have to seek the elf and dump it and analyze that process after being that binary after being done, but making sure it's only a looping kind of binary, but it has the shell code in the memory in the same workspace. So actually it is the shell code was injected. This one was injected from the another command which was deleted. So this you can see the similar code was there, and then this is actually the injections command that's being used. So this is not in our topic, and you can confirm this in the Luxembourg talk. But in this matter, you can see that it has the two stuff of the shell code being pushed, being executed. First is the stop. The stop is calling for the two syscalls. The first one is a syscall forking, and the other one is a syskill. The fork is making sure that you're being forked first, and then if you can't, then you'll be ended with a kill, syscall kill. And if things are when as per plan, the socket is started to be called there, and invoking another syscall for the bind, listen, and accept for the communication to the remote addresses. There are two duplicates is being executed there, and then yes, you can see there is a message being pushed in the RVX, and it is piped to the XCCVE, and then it will be exited. It is actually the bind shell. So the next example, the good version of the malware tech is making a good example of the shell code there. So I'm gonna use this for these exercises. Well, you can open that sample and analyze it in the router like this. You'll see the very interesting variable there as a for h, which is using it a lot, and it having a virtual alloc memory copy, which is a very, very intriguing calls for the Windows operations. And there is also the interesting strings there. Yes, let's see about these strings. Is it really a strings, or is it a code here? So I have to be sure about that. But it seems like the rest of the code is operations for the invoking that strings too. I'm not so sure. Let's see. Let's use the magic command to make sure there is no strings being involved in our analysis on results. So it looks like this is a looping command with a roll for being called from here, and this is actually the data that probably the aspects of flag. So it looks like it will be feeding to these roles. Let's confirm it first with our emulation here. I make a simple code by the different machines, And basically it's operating the same for the roll, letting it loop with the same conditions, rolling by the 5. And I just break it to any kind of the codes. I use a print for the syscall there, and dump to the RSI to see the flag is, and this is actually what the result is. So now this is another emulation using the ESIL. I'm using the sample of the strings to exe coming from the again the maltext site, and you can download it from here. The strings is started as usual command with the radare. It's loading the as a we know it's a exe file, PE files. So if you see the browse the binary, you cannot see strings anywhere. Let's check the functions, and then we'll see there's an entry 0 over there. Let's see where the strings actually started. Okay, try again with the iz command to dump all of the strings that possibly parsed. Then you can find it there. You go to the entry 0 and see there is a ASCII being pushed there somewhere, and it is starting from the ESP subtracted by the 28. And then if you scroll down, you will see it will be formed in this address. So all we have to do is using the ESIL. ESIL started from this entry point, and then with EEIM and EIP for the start counting, and it is a command that you can use. You can step back, step over, you can step until some address. I will use the EASU for going to this address for the EIP to extract the strings. Then going to visual mode again, you see the EIP is moving there, so we have to extract it like this. Here we are. Okay, in the next part, these are about the concept in defending our boxes. The more you prepare, the better your chance will be. So in this slide is explaining about how important for us to really aware about how the speedy rate for exploit discovery, disclosure, and POC development are used for the latest exploitation related tools. So shellcode is taking a big part of it as a trigger, loader, or stager, and the point is to get the intrusion to the system. So this is you can read about this. The rest is an essay for you as a takeaway, and the next slide is also a thought and an advice. Process injection tools and frameworks that utilize shellcode in its operations, having its shellcode generator built into the tool. These frameworks are rapidly developed so it can follow the recent vulnerable environment and involving its target ranges from endpoints to servers, mobile to IoTs, and so on. It's explained about the EDR2 over there. You can read about that. And this is about the details on how to handle as a digital forensic about the shellcode type of the exploitations. You have to understand about how it is infected you, and then you have to really involve in the research whether we are prepared for this kind of intrusion or not, and so on. Everything is important, like the logs. So it is having very good advice too. And this is the incident management handling tips for the shellcode related exploitation and intrusion. Basically, it's having a similar handling, but more delicate and more sophisticated for the threat level. So you need to be kind enough and more understanding to the victims, and try to have more communication with them, because they're not understanding what you understand there, and guide them to make sure that they understand what the risks are, and just making into some kind of discussion for anything that can be helpful for the investigations. My playbook for this analyzing the shellcode is for Windows is pretty much known, and more like any kind of malware. But for the Unix-based systems, especially for the servers, do not be afraid to get into the memory analysis. using the very dependable tools for the any kind of the platforms. r2con is the best tools that I know and that I'm using right now. And use the previous example is very good for you. And the three things that we're good: we can break the codes better, we can communicate with each other, and we can do the great OSINT. Now go to the special case. Case number one is a Magneto. Magneto is a shellcode that is formed to target the specific users in the in using the specific browsers and making a ping back to the specific host. And it is actually having a pre-exploitation stages, but not being explained here. And this Magneto shellcode is the end of the target. Then this is how. Anyway, this is how I analyzed Magneto at the time. I was using r2con in 2014, and then I posted in the page of the Melons DAY, and put those in the put this analysis result in as a comment, then making it as a comment writing there, and then just explain about how it goes and what kind of library it's called. It's using some has to translate the API of the Windows, and then I just calculate the hash, and then find the library and the function that actually being used, and write it as a comment, and then using the PDDA to dump the result to make it easier to read like this. And it will be a very good documentation to look over and over again. I didn't disclose this sheet before, just paste in the paste pane since this matter is becoming a public knowledge too now, so this is the way that actually being analyzed. So you can see all of the comment there are related to the opcodes in the left side, and then it's actually explaining in details about the operations of this shellcode is all about. The second one, we're going to the interpreter, but I forgot one thing. But this Magneto, it has two works here. The first is sending the ARP or sending the HTTP packets as a get commands. Second, the Peter bind shellcode in the ITW, spotted in the wild, and it is also using the hash table for the translation of the API of the Windows libraries and its functions. And this bind shell is listening to the port number 4444. And it's a kind of usual, but it's very interesting to see that many stuff in this interpreter is actually matched to the Magneto before. Poison Ivy has two kind of the exploit code. The one is based on the parsploit, and then the second shellcode is will be executed after the payload of the Poison Ivy is installed, and then this is the one of them, and it has many kind of the originality and variations. So I just pick up one as a screenshot, and write about the API functions used in the text below the screenshots. So it's a really difficult to analyze this post exploitation unless the status is still online, and then you can seeing it in the real time. The references, first is the resources for the shellcode. There are Venom, ExploitDB, and Packet Storms. And the second reference is a shellcode wrapper scheme that I'm using. You can use it for yourself too. I just marked the wrapper parts, and these are the interesting shellcode analysis, and then the reference that you can have. And again, thank you for having me. Thank you for Pancakes and r2con cool stuff, and rather development folks. And see you in the next part of the talk in the r2con, we're gonna be talking more advanced over there. Thank you again. Hello r2con, this is Unique Fix JB would like to.
Thank you for your presentation. So I'm happy to have you again in r2con. I guess that there's some questions around from the audience. So this is the first question that was dropped in the chat.
Okay, what is the shell code?
Can you answer it?
I hope so.
So the first question is, what is a shell code?
A shell code is, as per explained in the presentation in the page 11, I guess, it's a series of the array of the bytes that that is executables and usually made it very small, that can be executed in any kind of the part of the medium that make them being executed. So the purpose is varied, can be good, can be bad, mostly bad. And then in this talk, I was explaining about the overall of the shell code, mostly by the example with non-operational matters. That is the explanation.
Thanks.
For the longer explanation is in the page 11. Okay.
Any other question? How are you that fast? Was the stream pre-recorded? Any fancy clipboard manager?
Okay. The thing is, I have 30 minutes up, and I want to put many stuff in it. So with that speed of talking, demonstrating, and then it will be a video for this, and you can do the slow motion as much as you want after the video is published, so you can learn a lot from it.
Thank you.
If I...
Yeah.
Okay.
There are more questions? Why are you so fast? That's impossible to follow.
Okay, because I want you guys to have as much knowledge as possible within this 30 minutes. So I have to put everything. You can again, you can slow motion the video afterwards, and you can learn many stuff from there.
Okay. Another one. Another question. Will the slides of this talk be published?
Yes, in these questions, I think I will have to forward this to you, Pancake. And I agree for the publishment of the slides and the video.
Cool.
So please contact the Radare and the Pancakes about the publishment of these materials, and he will guide you. Video will be downloaded, from where the slides can be downloaded, and so on.
Cool, thanks.
Thank you very much. There are no more questions for this talk. It was amazing, and thanks for your efforts.
Thank you very much for having me, and appreciate your good work and the hard works.
And thank you for being awake very late at night.
Okay, goodbye.
Thanks, goodbye.
Bye-bye.
welcome back to the third day of r2con 2020. This time we are having a special R2 Wars competition. The thing is that someone found out a bug in a simulation for R2 Wars in R2, and this is basically exploiting that bug to win all the games in the R2 Wars competition. We'll make the rounds today. We had like a quick fix for the bug. We will also have a special thanks to the guy that found out the bug, and also we will give him a special present. And we will show the bug after the first round. So feel free to enjoy the first round, and you will see how it goes. Time to play. Okay, I will lower the music and show you the explanation of the bug that happened in R2 Wars. So first of all, I would like to show you the code of this bot. This bot was written by Kurt, and the name is Nico. You can see that, well, basically there is this script which I'm using for testing the R2 Wars bots. It's basically setting the stack address. This is used by your IAM. It's seeking to the 100 address, which is the entry point, and the stack is starting in here. So this is the code of the bot, and then it's setting all the registers for initializing the VM. So if we execute this script like this, it will basically start R2 with 4 kilobytes of virtual memory, and then including the script. So if I go into Visual, we can see that this is the code that is executing in the bot. We can step slowly. I will show the register, so you see the values of AIX, which is set to -1. And then we can slowly step down and see the rest. So it's setting the RSP to the address of the stack, which is the last address in the arena of the R2 Wars. And then there are two big values, which are set to RBX and RDX, and these are pushed. As you can see, this will be pushed into the stack, which is the text that you can see here on top. So this is the stack contents. So if I step, I will see that this code is being written. And after the second write, it will be jumping. So you can see that this jump is jumping into the stack, and you can see the new code. So basically the two previous pushes was writing this. As you can see, this is basically executing one rep, a bunch of pushes, and then a jump back to the pushes. So the thing is that this bot is jumping at the end of the arena, then so writing itself into the end of the arena, which is a very small payload, and then jumping around in there until it's filling all the memory. The bug that was exploiting in here is basically the execution cost of this instruction. If you type AO, you will see that we can get a bunch of information. And the cycles cost, which is how expensive is this instruction, is 1. This means that in one cycle, it will be writing basically the whole memory. So no one can compete against that and also it's wrong because writing a lot of bytes in memory takes a while. And the way that r2wars is working is that it will be basically taking some sleeps depending on how expensive an instruction is before jumping into the next turn for execution. So the quick fix was added, and we will make another run after this execution. So congrats to Kurt for finding out and exploiting this. That's so fun. The thing is, I think that a better solution, which will imply some fixes in r2wars, I did this pull request yesterday, and I hope that we will be fixing the r2wars during the day. And the fix can probably change the behavior of some other bots, but it will make more sense. We'll have to do a bunch of testing before doing that. So let me explain the new rules that we will be setting in r2wars. The thing is, we have like the sequels cost, but we now we have the ESIL cost. The ESIL cost is basically how expensive it is to execute a specific ESIL expression. In this case, this ESIL expression depends on the value of RCX, which is the one used as the go-to. Okay, so the RCX is determining how many times this go-to will be executed. As you see, right now it's 3000. But if we change the value of RCX to 3, for example, we can type again and check the ESIL cost. And you will see that now it's 72. We can also change that again, and you will see that the cost is different. So actually, this is more realistic because rep instructions will be behaving properly in the next version of r2wars that will be happening around the day. But the thing is that there was like a workaround for rep instructions in previous versions of r2wars, but the thing is that this bot was exploiting one of the remaining points that we didn't fix. So I think that it's time to get a ESIL cost into the scene. And yeah, we'll see how that goes in the second run. And congratulations for finding the bug. So I encourage you, everybody, for keep finding bugs in r2, keep exploiting them in r2wars, and keep having fun. And now we will have the second round, which is doing it with a fixed binary. Let's see which are the new results. Hey, some people is asking me how this ESIL cost is computed. I will show you the code minute as well as the explanation of how this code is working. This is still experimental, and there is actually an open pull request out of this, so you can check it out and give your comments and feelings on this. The branch name is ESIL cost, and this is actually the code. So if we jump into the CMD anal function, we can scroll down to ESIL cost, and this is computed using this new function, which is called ESIL _cost. And this is the implementation. It's pretty simple. So what it's doing is using the ESIL library to parse the ESIL expression. So it's creating a new instance, then setting up the basic thing, which is creating all the instances of the instructions and so on. Then it's setting EC as a user pointer, which is this variable, which is the actual cost. And then it's setting the memory read and memory write callbacks. So every time that the registers are being accessed, this is considered like a zero cost, but accessing memory takes some more cost. So let's see which is the actual cost for writing and reading. We can see that the memory write costs twice the length of the operation, and the read is the same as the length. So this is, if there is like a push of 4 bytes, it will be writing 4 bytes in the memory. And as long as it's a write operation, it will be a cost 8. And if it's the other way around, if it's for reading, reading memory, it's cheaper than writing in them. So it's considered like only the length. So it will be reading 4 bytes cost 4 cycles. The reason why we are not taking the registers into account is because some operations, which can be very simple, like a simple move instruction from x86, for example, it's changing a lot of registers. We can check that using our tool. So we can go and open the classical ls. We can see, like, for example, in this mob, we can check the cost, and the cost is 0. But if you go to the pop, the cost is 8. Okay, so the thing is, let's check the expression to see the ESIL expression of this shard is actually taking a lot of memory access, register accesses. Okay. The thing is that right now in the current implementation, there is no way to check if the shard is more expensive than a move or subtraction or something like this. But I think that this should be also taken into account. But I think that a shard mob or anything like this should be less expensive or much less expensive than doing a memory access. The thing is that actually this is not a real execution cost, but it's the execution cost inside the R2 Wars game. We can check other instructions, like for example this mob, which it's quite simple, but this one will be much more expensive. You can see there is a lot of side effects, setting all the register flags and so on. This is the current decisions that we took in order to get the ESIL cost computed. But I think that it should be also taking in consideration the types of operations that are happening inside the ESIL expression. You can check out the pull request. I will give you the link now. So this is the link. And actually, this is the QR code for opening the pull request. So feel free to check out the code and share your comments and feelings and ideas for it. Thanks. so welcome back to the R2 competition. The second round is over. You can see that the results are quite different from the previous round. This time there are no two players with the same score. We have the first position, Flacucho. Congratulations. He's running the ARM32 bot. In the second position, there is Anise, which is playing really good. It's also running in ARM32. And in third position, there is Fat Banana, which is running on x86-32. So congratulations to these players. We will now jump into the next presentation, which is in R2/C means cryptography from Sylvain Pelissier. I will make the transition and see you soon. You can start your presentation.
Okay, so thank you for joining me to my presentation. So today I will speak about cryptography and Radar-E2. So as you may know that reverse and exploitation often the analysis of cryptography. And I wanted to share with you that it has, in fact, helper commands which are already included in Radar-E2 or plugins, which are really nice to use when you're doing a reverse. So now I will show you practical use case where these commands are useful. And I also will present the inner working of these commands so that you will have a better understanding on how to use them and maybe how to improve them. So the first step during a reverse is to identify which algorithms is involved. And for that, usually crypto algorithm, I mean the public crypto algorithm, have constant, hashbox, or nonce, which are public and defined in the spec. So we can rely on this constant or hashbox to identify which algorithm is used. Just one quick example, Shasha, which is a stream cipher, which is now used in TLS, use a 16-byte constant, which is literally the string expand 32-byte k. And this string will be used together with the secret key, a nonce on a counter, and then will make the initial state. So if you find this string in a binary, it means that you will have certainly Shasha, which is used for encryption. So in R2, we have a plugin which uses Yara. Yara is an open source software developed by VirusTotal, and it was designed to detect malware. To do that, it uses rules which are quite flexible and quite interesting to use. And it will trigger if it matches this rule. For crypto, there is already a lot of rules publicly available in the GitHub of Yara rules, so you can go and find them. And to be able to use Yara in Radar2, you have to install a Radar2 extra plugin. So it's quite simple. You just run the package manager. You have to install Yara and Yara R2, and then you will have the command available in your Radar2. The rules are quite easy as well. You have to define the rule, give it a name, then you define strings, which is the string you want to match in your binary, and then condition. Here, the condition is quite simple. We just want the string, which is the previous string I showed you before, to be present in the binary. But it can be quite much more complex. You can use logical operator and so on. So I will show you a quick demo on how Yara works in practice. So here I have SSD firmware, which is loaded by another binary. And if we open this SSD firmware, we'll notice that everything is encrypted. In fact, the binary which loads this firmware will first decrypt it and then load it to your SSD controller. So if we open the binary which load the firmware, I will first clean the previous rule. I will add the rule I downloaded from the repo I showed you before. Then I can list all the rules which have been added. So there is a lot of them. And then I just scan my binary. It takes some time because binary is big, but then it tells me that it triggers some rules for prime constant, SHA constant, and AES. So it is a good indicator that the binary use AES for encryption. Then there is even an option to show you the offset at where the AES S box was found and the value which triggers the rule, which can be helpful to discard false positive. So this is an interesting tool for reverse. I have to warn you, cryptographers tend to reuse primitives, and it can you can have some more work to do. For example, if we go back to SHA, Blake2 is a hash function which was based on SHA, and it uses the same constant. And then r2con2020 is a password hash function which uses Blake2. So if your Yara rule trig for SHA constant, then you have maybe a bit more work to do to see which algorithm indeed it is. Then there is another kind of command in radar2, which is to compute hash or CRC. So it is named ph, so for print hash. There is already a lot of algorithm implemented with this function. You just have to print the help to see all this algorithm. If you don't want to open radar2, you can use hash2, which offers this feature externally, just in one command line. And there is another interesting command, which is /h, which will help you find a block which in your binary which match a given hash. For example, if you type /hmd5, then a hash, and then a block size, in this case 512, the command will search for in all the block of 512 bits, 512 bytes, if the hash, the MD5 hash, match the hash you've given as a parameter. So it can be really helpful if you found a hash in your binary and when you think it, or a CRC, and you think it's related to integrity check of part of your binary. Then sometimes you may have a RSA or elliptic curve key, which are used in your binary. So often they are manipulated in ASN1 format. So this format is quite simple. You have a tag, then you have a length, and then you have the data. So we can take advantage of this structure to parse your memory and to see if there is a key, a private key found in memory. So this search is implemented under the /cr command in R2. And there is a similar command which is called /cd, which will do the same search but for certificate, which is a bit different. So just to give you more information how this search works. So first, you have a chunk of data. You will scan if you find 3 bytes, which correspond to a version number, which is always the same for private key. But it's not enough for to be sure that it's indeed a private key. So then it goes backward until it finds the sequence tag. Then if yes, it will see if the following byte represents a valid sequence length. And if it's still okay, then it will continue, see if there is an integer tag after the version number. And then if in the case of RSA, there is a length which is valid for a modulus. And if all these constraints are true, then we have a good chance that indeed we have a private key in memory and we can print the value. So this search is interesting because usually private keys are stored encrypted in a file. You may have seen this kind of file where you have private key and then it's encrypted, so you cannot access the value. But sometimes you have a binary which will take this key, which is encrypted, have the passphrase to decrypt your key in the binary, will decrypt it and load it in RAM to use it later for decryption. So we'll see how with a demo how it works in practice and how we can find those keys. So here I have an example which is simple. It takes as an input a private key, and it will decrypt the file and print the text. So here the text is hello r2con. However, if we print the key, we see that it is encrypted, so we don't know the passphrase to decrypt this private key. So let's open the file. And I will debug it with the private key encrypted as an argument, and then I will continue and just until a function which will clear the memory. So I will hope that the private key is in RAM. Now I'm at this point, and I just first I have to tell the radar2 to search in the debugger memory, otherwise it won't find the key. And now I can launch my command /cr, and you see that it finds RSA key. So then I can just go to this value and take the key, and then I will be able to sign anything I want. So it's quite convenient to have this feature. Then sometimes, as we have seen in the beginning of the presentation, we have AES encryption. So AES works like that. It takes as an input a plain text and a key, which is secret. It will XOR the key with the plain text. Then it will go to the SBox, shift row, and mix column operation. And then it will XOR again the result with the second subkey, which is derived from a key schedule operation. The key schedule operation works like that. So the subkey 0 is your private key, which is splitted into groups of 4 bytes. Each 4 bytes are XOR with the last 4 bytes of the key, which have been going through root word, subword, and r2con operation. And this is r2con operation, not r2con. And then the result is the first first byte of the next subkey. And the idea to search AES key in memory is to use this relation, to use this 3 group of key, and to see if they verify this relation. To go a bit deeper, we will scan the memory. We'll take the first 4 bytes. We'll XOR them with the last 4 byte process through the 3 operation, and we'll see if the result equals the first 4 bytes of the next subkey. And if yes, there is good chance that you have a AES key in memory. As what we discover in practice is that this rule works, but sometimes you have false positive. It's not sufficient for to discard all the false positive. However, we can just exploit the next relation of the key schedule and see if the first and the second relation are valid. And then there is a really, really good chance that we have a AES key in memory. So that's how it is now implemented in R2. So you see the first relation at the beginning, then the second relation, and we return true only if the two are true. So now radar2 support all the 3 key size for AES. And this is really convenient because you can apply this search on debug memory, process image, memory dump, whatever you want, as soon as you can open it in R2. And I didn't invent this technique. It already exists in 2 other tools. The first one, the oldest one, is called AES key find. It was developed for a cold boot attack. So it allows you to have error in your key schedule. Even if you have bit flip, not a lot, still it will output a correct key. However, it does not support, as it is 192 bits key. And there is as well another tool which is called interrogate, which will search key for AES, Serpent, to fish, and it will also implement the key search for RSA as I presented before. So now a demo of how it works in practice. So if you remember the first example with the SSD firmware, I don't have this SSD here, so I made a small program which reproduces the encryption, the same encryption, and simply it takes a plain text, encrypt with a key, and output the ciphertext. It's quite simple. Now we'll debug it with R2. And I will, first I have to set up the search in the debugger memory. And then I will continue until, oh, can you hear me? Okay, I will continue. So I will continue until the AES encryption is done. And just before the encryption, the key schedule has been computed. So then I can search for the AES key. And here I have the key which is found. So I will copy it for later. Next, as soon as you found a key, you will decrypt data. So the command which are implemented for this are under WOD for decryption and WOE for encryption. And you have to open the file in write mode because the result will be written directly in place. So you have to be really careful because you will change your binary. And again, if you want all the list of supported algorithms, you just have to print the help of those commands. So go back to our demo. So we go back to our firmware. Now we have found the AES key. So we can open in write mode the firmware, which is encrypted. Then I will decrypt with AES CB and the key I copied before. And then if I print, I have the string which are unclear, so the decryption happened properly. So this was a small round of crypto command which are included in R2 so far. I found it really helpful because you can work on crypto directly in R2. You don't need external tool. You don't need to copy your dump to somewhere else. And it's also easy to extend because if you have a new algorithm, you just have to write a new Yara rule, for example, to detect it, or you just have to add your algorithm in R2, and then it will be available for decryption or encryption. So it's really convenient. So if you want to contribute on that, it's easy. You can add your rule in Yara rule repo. And there is already many rules dedicated to crypto, so it's nice. Even not for crypto, but for malware, you can use it in R2. If you want to add new algorithm like SHA-3, SHA, which are missing, you can implement them in libr-crypto folder. And if you want to add or improve key search algorithm, you can have a look in libr search folder. So I would really thank you, all the organizer of R2. It was really going almost smoothly, except at the beginning of the presentation. And if you have any question, I will be happy to answer them in the Q&A.
Thank you, Sylvain. I don't know if you have any question. Did you check the URL?
Yeah, there is one question.
Okay, I didn't open it yet. Just 1 second.
Sure.
Okay, can you share my screen?
Yeah,
Yeah. Can you stop sharing? So.
Yeah.
Do you see the question, Sylvain?
Not yet.
You're not sharing the screen yet.
Sorry. 1 second, please. Okay. Do you see it now?
Yep. How does it compare?
So the first question is, how does it compare to IDA's crypto stuff?
I don't know a lot either. I'm not the best person to answer that, but I think there is one plugin which is similar to Yara. So you have rule and you detect crypto constant. I don't know how it compare, if it's more complete in IDA or in R2. For the key search, I don't think it's implemented in IDA. I have never found anything speaking about that. But again, I'm not the best person to ask.
Okay, thank you. Yeah. So do you know of malware or CTF challenges that obfuscate crypto algorithm magic numbers? So it's difficult to know which algorithm is being used?
So it's not obfuscation, but for example, AES, you can write white box and you can use T-table. T-table should be detected by Yara, but white box won't because everything is mixed with the secret key. So AES in white box won't be detected, and you can do white box for a lot of different algorithms. But yeah, like masking or secret sharing, like splitting the constant, I've never seen that in challenge or in. I'm not working on malware anyway, but in a real product. So yeah, could be interesting.
Yeah, indeed. More questions. So this comment can also find hard-coded keys in binaries.
So you have to have your key schedule computed in memory. Usually you store the command as it is in your binary, and then at the runtime you will expand it for AES. For RSA, yeah, it will find the key if it's in clear, but yeah, if you have the private key in clear in your binary, then it means your binary was not so secure.
Cool.
Yeah, I think there's no more questions.
There are no more questions?
No.
Okay. Thank you, Sylvain. It was an amazing presentation. Unless you want to add something else, I think we are done with the presentation.
Thank you very much, and thank you for all the organization at you2.
Thank you. It was great to have you.
Thank you.
Hi there. Give me a second. I just have to open the Slack in a new window, the chat. So, hi. Welcome to the workshop Semi-Automatic Code Deobfuscation, and thanks for having me, Pancake. I've been giving a similar workshop last year in person, and today it will be more of a live coding and a live hacking and thinking loud. And the only way to answer questions is the live chat. So I will keep an eye always on the live chat on YouTube. So just ping any questions there, and I will answer them during the next 2 hours. So a few words to my person. I'm a reverse engineer, a trainer, a security researcher, and a former PhD student. So I basically give trainings on reverse engineering and software deobfuscation. I did PhD research on code deobfuscation, fuzzing, and bug triaging. And currently I'm working at mProof, where I design and evaluate code obfuscation techniques. And in the following in the following 2 hours, we will do a live coding. So basically, we will have a look at some APT malware that is called Xtunnel, and it will contain a lot of similar obfuscation techniques, namely mainly opaque predicates. And we will do a live coding and using symbolic execution and SMT solvers to basically automate the detection of opaque predicates, and afterwards we will remove or patch them automatically out of the binary. And for this, we will, after the 2 hours, we will publish the slides and the code at this URL, and we will paste it later on. So, and again, if there are any questions, just ping me in the Slack, in the chat. So let us start. We have there will be no material for the workshop. There will be everything. So I will publish the sample and something like that later on in the Git repository. This will be our live coding now. So we basically have a sample here where we have the file and we have a start address. And we will just first have a look at the sample in Kata at this address. So copy this address. We open Kata. And now it will take some time, about 40 or 50 seconds, because the binary is rather large. So let us just wait. So it should be finished soon. There you go. Now we open Kata at this address. And what we will see here is that we have a rather large control flow graph. However, there is something buggy because that's not everything. So normally this function has around 800 basic blocks. So, and these are way less than a few hundred. So what we'll do, we will open Kata again. And this time we will disable the automated analysis. And we just load the binary. And now we basically will just increase the analysis depths of how many basic blocks we will take and analyze in a row and set to some large number. And then we manually define a function at this address, and then we just jump to the function. And if we do that, we have the function now. And if we scroll out, we see that is now a little bit larger. So now we see our 800 basic blocks or something like that. And the thing is, in the end, after the workshop, we will remove most of the basic blocks because they are just dead code. They are just some kind of control flow obfuscation that is used by the malware authors to basically hide what they are doing. So if we have a look at So basically what this control flow graph performs has a lot of opaque predicates. So what is an opaque predicate? So basically assume we have some kind of conditional statement like f(x) is equal to x plus y, then we return 10, otherwise we return 20. So if we look at that on a control flow graph, we have some kind of diamond graph where we have the conditional statement on top, then one basic block where we return 10 if the condition is true, and another one where we return 20 if the condition is false. So in this case, this condition can never be true because x cannot be the same as x plus y. There's no arithmetic case where this can happen. And therefore, we basically know that this is an opaque predicate. We know that this is an opaque predicate because this code here can never be reached, because this can never be true. And something like that is a lot in this graph. So we can just have a look at some statement. So let me just look for it. So let us take this one. So basically here we read two variables. We do some arithmetic operation and we do a conditional comparison, jump equal, based on the two values here. And we can just say, for instance, let us assume that this is variable x and that this is variable y. So this code basically breaks down to we multiply x with x and multiply it with 7 and store it in ECX. And afterwards we decrement it. So basically this would be x times 7. And this would be x times 7 minus 1. And we store this in ECX. And if we see, we use this in the comparison here. And we compare it against EAX. And EAX is basically just the EDI, what is our y, and we just multiply it by itself. So basically we have y times y. And therefore, based on the result of this comparison, we jump if the two values are equal. So in other words, we can basically say that the whole predicate or the whole jump condition is x times 7 minus 1 is equal to y times y. So this is basically what we recovered. And now we want to know if there's any possibility such that can be true. So we want to know, is this an opaque predicate or is there any possibility such that this can be true? And for that, we will use an SMT solver. So an SMT solver is basically just a magic black box that can solve bit vector equalities and inequalities. So for instance, if we open a Python shell and we use the SMT solver Z3 that is also used by the talk that was yesterday at the r2con. We basically say we can define as two variables of a fixed size. So let's just say we have x and y is of size 32-bit, y 32-bit, because the variables in the registers here are basically 32-bit variables. So we define two variables of size 32. And now we define two formulas, f and g. And f is basically what we derived as the first formula. We thought it was x times 7 minus 1. And g was y times y. So we have f, we have g. And now we want to know if f and g can be, if there's any possibility such that f and g can be the same value. And for this, we basically say we add to the SMT solver the constraint that f should be equal to g, and then we can just check it, and we see that it is unsatisfiable. Unsatisfiable means there is no way such that there is no possibility for f to be equal to g, since for all possible inputs for x and y. So in other words, there is no possibility such that these two values become the same. So let me get you a counterexample. So let us just check if x plus x is the same as y plus 10, for instance. Let us do something like that. So, and here it says it is satisfiability. There is some solution. And if we have a look at the solution, we basically see if epsilon is 0 and x is 5, this holds. And obviously, 5 plus 5 is the same as 0 plus 10. So, in other words, in this example, the SMT solver was able to find a solution. And in this example, on top of here, there cannot be any solution. In other words, we use the SMT solver to do a hard proof that this branch cannot be taken. In other words, we know that the true branch here will never be taken. That if we visit this basic block, we will always go to that one. So, and in the remaining parts, we want to automatically identify all local opaque predicates in this control flow graph and automatically patch them. And for this, we basically use symbolic execution and SMT solving. Solver.model gives me only one solution. So, for instance, in this case, it gives me only one solution. If I want to have more than one solution, I can just enforce it to give me a different solution. So I could just add, for instance, x should not be 5, and then I can check again. And now I get x is equal to 0. And if we have a look at that, there's something wrong. Oh yeah, I resetted the solver. So I just enforced that x should be not equal to the solver. So basically, if I add this constraint again, and do the check, and check the model, then I basically get something different. And this will basically now overflow here because we have a bit vector of size 32-bit, and if we add these two x twice, we basically get a number larger than 32-bit, and if we just reduce them by taking the power, by taking the modulo of 2 of the power of 32-bit, we get the same result then. So, and now coming back, we want to automatically identify all the opaque predicates. And for this, we use a scripting language that is based on, that is in Python, and that is based on the reverse engineering framework Miasm. So basically Miasm is reverse engineering framework from French guys. It is completely open source, and it has a lot of opportunities. It has its own disassembler, it has its own control flow graph analysis, it has its own intermediate language comparable to ESIL, it has its own SMT server backend, and it has, that is the greatest thing, a fully flexible and fully flexed symbolic execution that is really useful for our case today. And we will interact now with Miasm and Kata to basically simplify the opaque predicates more and more. So first, we start with a few imports, and we just hard-coded the file path and the start address. The first thing that we want to do is that we want to open the binary for analysis, and then we want to disassemble the function. So to open the binary, we basically define just a container. A container is basically a binary file stream that reads the input file and that's all. And now we have some instruction. We can just check if it works. We say there's one argument missing. So the thing is, we also have to define a symbol table that basically keeps track of all the possibilities of all the locations that have been disassembled. So basically the basic block labels. So we just define it by initializing a location DB. And we pass it as a parameter, and then we should be fine now. So, and after that, we also need some kind of abstraction, a CPU abstraction, because we are working on multi-architecture analysis framework, and based on the binary, we pass and read the binary, and basically we define our, we have to know on which CPU architecture we are working. So we basically say machine and container.arch. If we just print container.arch, we just see that this is a x86 32-bit binary. So, and this is just a 32-bit x86 abstraction. And now we want to disassemble the function. So we initialize the disassembly engine. And also provide it with the bin stream. So basically with the binary stream of the binary and also the location DB. And now it should work. Looks good. And now we are able to disassemble the function. But let us first disassemble basic block. So we say the block is mdis, disassemble a block, and we provide it with a start address. So, and it's basically the start address that we defined on top of here. And then we can just print the block. And if you do it, we basically see we are at this location. We have a push, we have the move, and we end with a jump to B20. And if we have a look at kata, at the first basic block, we basically disassembled the whole first basic block. So, and now we disassemble the whole function. To disassemble the whole function, we say here that we do this multi-block. So basically we disassemble multiple blocks. We start at this address and do a recursive descent algorithm until we get the whole control flow graph of the function. And then we, for instance, can just print the length of the number of basic blocks. So if we do that, we see that we have 816 basic blocks. We can also dump the disassembly here. So for instance, we can just write a file, AFM graph, and write it as a dot file. I will explain in a few minutes what a dot file is. So now we wrote the dot file. So, oh no, I think there's a B missing. Ah, no, this is a function. So basically, what is a dot file? This is basically something as LaTeX for graphs instead of for documents. So we can just define some edges, something like that. And then we open an interactive graph viewer and we just get the automatic layouting. And if we want to add a loop between 2 and 3, we can just do so by adding 2 more edges. So 2 should go to 3 and 3 should go to 2. And if we do it again, then we have a loop here. So this is the main idea of graph layouts, of dot files. We just describe edges or how basic blocks should look like, and all the layouting is done for ourselves in the background. And we basically Miasm does the same by exporting graphs exporting control flow graphs into dot files. So, and if you have a look at the file, it takes some time because it's a large graph. So we see these are our 800 blocks. And if we zoom in at the first one, we basically see that this is our normal assembly code of the function. So, and this is the thing. Now let's have a look at the basic block with the opaque predicate. And just for now, let's fixate on the single opaque predicate. Where was it? There you go. I just copy the address. Then I uncomment that. I change that to block again. And now I just hardcode the address here. And then let's print the block. And now we just see exactly the block that we know is our output predicate. What we want to do is that we want to automatically derive the condition, the arithmetic condition that we derived by hand. So we analyzed the code and said it is x times 7 minus 1 equal y times y. And we want to basically automate this such that we have a formula that we can automatically give to the SMT solver. And for this, we have to do one more step. We have to convert the assembly code into an intermediate language that is similar to ESIL. So it's just the miasm intermediate representation. And for this, we define another layer of abstraction, namely the intermediate representation. And we call it IRA for intermediate representation analysis. And let me just have a look. I don't know the syntax. It's basically this one. So basically what we do, we initialize the intermediate representation, and then we add the control flow graph to the intermediate representation. Also basically in this term, we would add a single basic block. I don't know if it works like that. We can just check it. Otherwise, we go back to the control flow graph. So I think there's also an add block. We can do something like that. We define a new IRA CFG, and then just check if this works. It works, and then we can just add block, and we add the block. This is the preset. Okay, let's do it the other way. Let's say we disassemble the whole function, and then we basically we add the whole assembly graph to the control flow graph. And then we can again print the graph, and this time we say it is the ER graph, and we do IRA CFG here. What's now happening is that we transform the assembly code into an intermediate representation that enables us to perform automated reasoning on the language because it is more explicit. So we will have a look at that. it's a little bit larger since it is more explicit and the graph is itself rather large. So, but in the end, we have explicit formulas for all of the different flags. So for instance, if we have an addition performs not only the addition, but it modifies the zero flag, the overflow flag, the sign flag, etc. And this intermediate representation graph basically includes all of the side effects that assembly code has. And if you just zoom in into one basic block, it really lags because the graph is rather large. So we basically see here that we have, this is an XOR, and that we have all the flag updates here, and then we have a jump, and that we have everything explicit. So basically, this is not made for human readability. This is made for automated analysis, such that we can do symbolic execution on that. So, and now let's start with symbolic execution. Symbolic execution is basically some kind of computer algebra system for assembly code or for an intermediate language. So basically, assume we have the formulas, we have the following code: x is x plus y, or x plus 10, and then we have y is equal to x plus y, and then we have z is equal and y is equal to y plus y, something like that. If we symbolically execute that, we basically will remember all the intermediate values and propagate them. So in other words, let's call this 1, this 2, and this 3. And then we have a state map in symbolic execution. And the state map basically has for each variable some kind of mapping that represents the current value of x and y. And initially, the state map is, for instance, x maps to x and y maps to y. And now we take the first formula, and this can be basically rewritten or understood as state map from x is assigned to state map from x plus 10. In other words, here we look up the value for x and replace it and add the 10. So basically here we have x plus 10, and so this is x plus 10. And then after we evaluated the expression, we assign it to x. In other words, at this case, we just write here x plus 10. If we now take the second formula, we basically do exactly the same. State map from y is equal to state map plus x plus state map from y. And we know y is y, but x is x plus 10. In other words, we just know that in this case, x is x plus 10, and we now assign it to y. So basically, after step 2, y holds this value. And then again, we do the third step, where we have state map from y is assigned to state map from y plus state map from y. We know that y is z, so basically we know that this would be z plus z. There's one more thing we can do. We can know that 10 plus 10 is 20, so we can do the constant folding here. And so basically we would have x plus x plus so x plus x plus y plus 20. And we would take this expression and state it into the map. And now we can say, after symbolic executing these three values, we basically can see that x is x plus 10 and that y is x plus y plus 20. And this is the main idea of what symbolic execution does on an intermediate language. And in our case, we will basically use that to automatically derive the opaque predicates formula. So let's just do it. We init the symbolic execution. Don't know its parameters. It's just the intermediate representation. So I think that should work. Let's test it. Looks good. And now we can basically do sb dot eval run block at. So basically we say that the symbolic execution engine should symbolically execute a specific block at an address, and we can now provide the address. And for instance, we can use, we will now use the basic block that we used in kata. This is this address. So, and afterwards, we can dump us the current state. So basically, we dump us every change that has been performed by the symbolic execution engine. And if we have a look, oh, there was one parameter missing. It takes the control, the IRA CFG and an address, fair point. So, and if you have any questions, I can use the time for the waiting time to answer questions. So, now we see we have a lot of formulas. And basically, we are interested in mainly one formula, namely the jump condition. So basically, here you see very explicit what's going on. So if we have a look at the code again, we basically would have intermediate values for EAX and for EDX and also for EBX and other things. And we are explicitly interested in the jump condition. So we can just say we want to know and just print the E. And if we do that, we will now get a larger formula here that basically is the thing derived in intermediate language. So we can see here, here's a question mark. And the question mark basically says everything before the question mark is a conditional statement. And if the conditional statement is true, we will go to that address, and otherwise we will go to the other address. And now we have a look. We see here we have a read from this memory location, and we multiply it several times. And here we multiply it with 7. And at some point we should also see, here we see the check for equality. Here we basically add the -1. Here we basically add the -1. It's just an addition of the negative value of the negative 32-bit value. And here we see the comparison with the other thing, where we have this is the y times the y. So in other words, we automatically derive the formula. And now we can use also that to pass it to the SMT server. No, so basically the state map will go on this works on the basic block level. So basically, if we would do symbolic execution on each basic block, or we would do it on a row of basic blocks or something like that. So it will never work on endless loops because the analysis is just rather limited on local parts. But it works so if in the end you would have to do some loop unrolling and stuff like that if you want to handle a certain amount of loop iterations. So now we have this we symbolically derived the address for this we derived the jump formula, and now we want to check it with Z3 if this is an opaque predicate or not. For this, we first must translate the expression to Z3. This is rather easy. So this is symbolically execute basic block. This is rather easy. Translate to Z3. We just define a translator, and then we say translator from expression, and we just pass E. And if we would just print it, we would basically get the translated expression into Z3 that can just interact with the SMT solver itself. I closed the chat. No, it's the chat. So, does it run? No, it doesn't run. I think yeah. I should print the correct one. So, and now we basically see it has been automatically translated into Z3. And that means we can do exactly the same. We can now go and import Z3 and add our solver logic down here. So we can say we define a solver, and then we know that this conditional statement has basically two different return values. If the condition is true, it returns the one thing. If the condition is false, it returns the other thing. So, and basically, and we access these things via source 1 or source 2. So basically, the E has our expression E, so it's the jump statement, has the form cont source 1 or source 2. If cont1 is true, we return source 1, otherwise we return source 2. And we can use that to basically check the SMT solver. We can do add, we translate it, so we don't need it there. We translate it, and it should be equal to source 1. So we can basically here do E dot source 1. So what we enforce the SMT solver is that the jump statement, that the condition should be true such that we can return this one. And now we can see if there's any possibility for that. And there you go. We proved that this is unsatisfiable. So we automatically proved that basically this part of the jump condition to source 1 can never be taken. So in other words, we know for sure that this is an opaque predicate. So basically we say this should be Z. And we can also check it the other way around. Let's just copy that, put it here, just uncomment it for a few seconds, and let's just set it to source 2. And now it should be satisfiable, because it's a jump, the code itself performs a jump equal, and we proved that it cannot be equal, so it must be unequal. And here we basically proved that we can take the other direction. So in other words, we are able to use that on a basic block level to prove if a basic block is an opaque predicate or not in this scenario. And now we did this on a small scale. We want to do it now on the large scale for the whole function. So for this, we will refactor the code a little bit and basically write our function. So we basically define a function, def branch can be taken, and it basically gets a condition or an expression, and it gets a jump target. So, and there we first define a solver. I can delete that code, and we define the translator. This code, and then we basically say we just can do solver add translator from expression is equal to translator to jump target. So, and then we basically return solver check is equal to sat. So if it can be taken, let's do it the other way around. It cannot be taken. So if it cannot be taken, we basically return true. And if we know, if this function returns true, we know that we have an opaque predicate. So let me just test the code. Let me do it here. Let me remove that. And let's just branch cannot be taken, and we basically perform the E and E source 1. And now we should expect that it returns true. And here we see true, so we know now our function works. It basically tells us if this is an opaque predicate or not. So if one branch can be taken. If he switches to the other branch and we just do it, then we would expect that we get false. And here you go, we get false. So, and we can use this as a primitive. Let me just do a few more comments. So we will place this somewhere above, on top here. We do the symbolic execution. This is fine. And we basically do it here. So let's do this in an let's say we have an opaque predicate if branch cannot be taken E source 1, or if the other cannot be taken, source 2. So basically, if there is one branch that cannot be taken into one of the directions, so if there's one basic block that is a conditional branch that can only go into one direction, we know that we have an opaque predicate. So, and let us just check if it works. Print opaque. And it says we have an opaque predicate. Okay. Then we can change this to address. And what we do now is we do this part in a loop. So by walking over each basic block in the graph. So we do for basic block in ASM CFG. We initialize the symbolic execution freshly, such that we would just perform the symbolic execution here on the basic block level, and by initializing it every time, we basically reset it all the time to a fresh instance. Then we symbolically execute the basic block, and then we check if this is an opaque predicate. We have to get the address of the basic block. So how do we do that? Well, we basically can just see address is basic block dot lines. If we access basic block dot lines, we access the instructions we basically access the instructions in the basic block. And the first instruction is always the address of the basic block. So if you have a look here, this is the first instruction of the basic block, and therefore it's the address of the instruction is the address of the basic block. So we just get the address, get address of first basic block instruction, and then we symbolically execute the basic block, and we see if we have an opaque predicate or not. So, and we see opaque predicate at can do it like that, and we can just see what's happening. It will break now because we have to handle a special case, but perhaps we go through and have some that's the thing. We have to first iterate over all the blocks, and if we do it again, we have this error that that basically there is some expression that has no condition source 1. What does it mean? So basically, if we have a look at the control flow graph, we have two kind of basic blocks. Those who are conditional jumps that have basically two different jump targets. And then there are also basic blocks that just have a single ancestor, a single successor. And we have to check if the basic block that we are analyzing is basically has two entries. So basically, if we have a conditional jump, we have to have a conditional statement, and we just have to check that or ensure that we have conditional statements and ignore cases like this jump here. And to do so, we basically can say if not E is condition, then we just continue. And now it should work, hopefully. And you see, it finds some opaque predicates. Before we analyze the whole function, let us just add a counter. We initialize it to 0. And just increment it by 1 all the time. And finally, we print just the opaque counter. And now we can just see how many opaque predicates are in there. And I think this will take about, yeah. So this will take about 40 or 50 seconds or 50 seconds or something like that. You see it's quite a lot there. So remember the whole function has around 800 and basic blocks. And we see that 100 of them, so 1/8, is just opaque predicates. So if we would remove all of these blocks or all of these jumps or patch these jumps, we would have a much easier control flow graph. And that's what we want to do now. So remember 105. So in other words, most of the branches here are just completely useless because they are opaque predicates. Let's have a look at such an opaque predicate and how we would patch it. So the idea would be, let me find the commented one. Let's just take one. This is another one. You see this is very similar, if not the same. We read two values, we multiply it and by 7 and decrement it. Yeah, this is exactly the same opaque predicate, just with different memory locations. And then we have the jump equal again. So if we have a look in flatline code, it basically says, if this holds, we jump. Otherwise, we take the false case, which is the false through. So in other words, if this never can be equal, we never jump. In other words, we can always take the false through. So in this case, we can just knob the jump, because we know that we never take the jump, and we can just enforce the false through to be taken, the false branch. If it's the other way around, if we never take the false through branch, but ever take the jump, we would have to, instead of knopping the instruction, hard code the jump into a single direction. So let's first just see what kind of opaque predicates we have. So basically here we check if it can be taken into the one or into the other direction. Let's be a little bit more explicit here. So let's take this one, do a pass, and do an else if, and or elif, I don't know if it's Python, elif, yeah, and do a pass. So, and let's do it like that. So in both cases, we want to increment the opaque predicate counter, but we have some additional knowledge. We know, based on the structure of this condition, we have cont source 1, source 2. We know that if condition is true, we what do you mean by analysis hints instead of patching? So instead of, so basically, so while you answer, I will go on here. We know the condition. If the condition is true, we always jump to source 2. So we have the guarantee that source 2 here is always a false through, and source 1 is always a jump. So we can turn around this. We know that if we never go to the jump, so if this is an opaque predicate, we know that let's do it again. So here we know that the jump is never taken, because source 1 always jumps, and if source 1 cannot be taken, we basically never jump. And the other way around, if we cannot reach the false through case, so this would be the false through, and this would be the jump. Here we know that we always jump. And now let's have a look if we always, how these opaque predicates are distributed. If it's always Z1 or if it's sometimes also Z1. And we can just write it into a file. So you see it took 50 seconds nearly. So let's wait again. So if we get to do, we see that the jump is never taken. We can just grab for for always. There's nothing, so we know for sure that we always take the fall through, that we never jump. That means for patching that we have the guarantee that we never have to handle the jump here, so we can just always patch this. And that's what we want to do now. We want to always patch the jump if we find an opaque predicate in the binary. So let's do it. Dum, dum, dum. So, well, we need a few things. First, we need so basically we know that we are never here. So we are never here and we are always here. And here we need to first get the jump instruction. To get the jump instruction, we can do a similar trick like that. So basically, we know that basic block dot lines is the list of all instructions of the basic block. And to get the address of the basic block, we took its first instruction. To get its last instruction, to get the jump instruction, we can basically just fetch its jump instruction. So, and let's just verify that these indeed are the jump instruction. So we don't, fair enough. We don't need the whole run. It's just, if we see a few jumps, we are fine. So jump 0, jump 0, jump 0, jump not 0, this is fine. So we know that we have a jump instruction. So we have the jump instruction, and now we want to patch it with a knob. So patch the jump instruction with a knob. Knob is basically on x86 \0 or the hexadecimal byte 90. So, and knob is basically no instruction. So, however, we don't. So to do that, we need first the address of the jump instruction. That is easy. This is just jump instruction.offset. This is the address. But if we have a look at the sizes, come on. So if we have a look at the sizes, we see that the jump instruction is larger than a byte. So in this case, it is 2 bytes. So, and we would have to patch both bytes. So what we need there is basically we would need its, the instruction length. And we get the instruction length by basically having a look at its bytes. So we can do print jump instruction dot b, and this is basically the instruction bytes. So you see here they are. And now we basically want to iterate. What we want to do is that we define a dictionary of byte patches. And now we basically work over the address of jump instruction. So basically, we work for index in range address of jump instruction until address jump instruction plus the length of the jump instruction. So, and we walk over that range, and then we basically say patches from index is 90. So this is a knob. So we basically walk over all instruction bytes and replace them and set them to 90. So, and finally, we have to open the file. So basically we have to read the file, this here, and patch all the addresses. So we can just do it. Patching. We basically can go and open the raw file. So we just call it raw bytes, is open we read the content and we store it in a byte array. We store it in a byte array because a byte array is a mutable data structure. So we can basically store it. And so basically we can read raw bytes. So then we apply the patches, and then we write or save patched file. That's basically all. To save the patched file, we can just open a new file. Let's store it under samples patched. Samples patched in write binary mode, and then we just write the raw bytes. So without the patches, I can just disable the whole loop just for testing purposes. So since we don't do anything here, the MD5 sum should be the same. Let's just test that. No, there is no any reason not to do that. So yeah, you can also use R2 for the patching and do all the same. Yeah, that's completely true. So if we have a look at samples and we have a look at patched, it's exactly the same as the file itself. So in other words, we are fine. So now we have to apply the patches. So this is basically raw bytes. Raw bytes index. So basically we work for index byte in patches.items. There we apply just raw bytes from index is equal to byte. And now we can disable this and it will automatically be patched. It's just, let's test it again. We disable that again. So let's just define patches as at the first address. Let's just do an FF there. So we basically now would overwrite the magic byte. I think it's items. So if we have now a look with the file command at patched, it just says it's data. And if we have a look at the first byte, we see that the first byte is FF. So we know our patches work fine. So the patching code down here works fine. We can remove that and we can just do the same thing again. We disable that. Now we fill our patches dictionary on the fly and afterward we apply it down here. Starting patching. So let's do it. No. Well, yes, this could be. The question is if this is any kind. Oh, wait. There's a bug. Oh, yes. I have to walk over the instruction bytes. There's a .b missing. So the question is if this is a performance optimization of the obfuscator, such that the opaque predicate always takes the false through and never takes a jump. So yes. So basically you can understand it like that. This is for sure one of the side effects of that. But I'm not sure if the authors had exactly that in mind or if it's just random. Because if we would have a closer look at the opaque predicates, here we see that they always apply the same opaque predicates. So this is the same comparison as this one, what is the same as the one that we already analyzed. So we have the same opaque predicate. So we know that they build their opaque predicates based on arithmetic identities, but we know that there are an infinite number of ways how you can perform arithmetic identities such that they will be that they represent opaque predicates. But the authors here always applied the same opaque predicates, and so I don't understand the reason why. So to answer your question, they probably could have done this for performance optimizations, but I'm not sure that they had that in mind or if it's just random. So if we see we have one problem. In the patching, we basically say that we are out of range. So basically the raw bytes are out of range. What does this mean? So basically, the thing is, we have two different representations here. We down here, we read the binary file from the file itself. So we have the raw binary file. However, the disassembler and miasm and other things basically have the virtual show the code in the virtual address space of the binary. So basically, if we enable addresses here, there should be. So basically all these addresses are basically just file offsets, and these are loaded into memory here. And what we did is we used as indices the virtual addresses. However, we would have to use the file offsets. And basically to convert the file offset, to convert the virtual address to the file offset, we can use the function from YASM. So they basically have an API function that basically says we access the container bin stream and then we have virtual to offset. So, and what we just do is we just rename this to offset of jump instruction. And we basically call this function, and basically to obtain the file offset from the virtual address here. And if we do that, the code now should work for sure. Minus I'm too dumb. Yeah, exactly. That's so basically what the question is: what happens when the binary has a different base address from 0 and the instruction addresses are not relative to the base address? That's exactly the case that we have here, and therefore we handle it now. So you would have to convert it then, as we do. So yeah, exactly. This offset, zip now offset of jump instruction. Okay, now it might work. So, no error, they patched it. Let's check that it is a valid file still. It's a valid ELF file, nice. So we can just open it in Kata and see what's going on. So we just open a second instance and open now the patched. We disable everything again. And now we apply the same hack as before, that we increase the analysis depth and disassembly only the single function. And there you go. And this is the remaining function compared to that one. So this on the left-hand side, we have all the function graph with all the opaque predicates. And here we have the remaining function graph after we patched all the opaque predicates. And if we have a look at that, how it looks like, we basically see that we have some knobs, for instance, here. So the checks are still in there because we don't know. Perhaps they are used something later. Perhaps they set some values that are later used for calculations. So we cannot just remove them easily. But we know for sure that we can just patch this jump. So, and because of that, we basically have the whole checks in again, but we have removed all the conditional jumps. And in the end, we have a much more simple control flow graph. And this is just one example. So basically, this was just one function of the binary. The binary itself has in total, and this function had 100 opaque predicates. The whole binary has about 50k opaque predicates that are all of the same, of a similar way. If we would basically apply the same algorithm, the same thing that we used here on the whole binary, we would basically deobfuscate the whole binary itself, or at least remove all the opaque predicates that we can find with that technique in the binary. And this is about 50k. So this is basic. So let me recap what we did. So basically, we had a malware sample where we just noticed that they have a very large control flow graph. And then we identified manually that there is something that looks like an opaque predicate. And then we manually verified it using an SMT solver that the branch cannot be taken. Afterward, we used miasm to first disassemble the whole function and transform it into intermediate representation. And then we walk over each basic block, symbolically execute it, and if it is a conditional jump, we basically check with an SMT solver if we can, if this branch can be taken or not. And if it cannot be taken, we know that this is an opaque predicate and that we can patch it. And then we basically applied the patching, and afterwards we get a cleaned binary. So this is the main idea that I wanted to show you, and that uses a combination of different techniques to apply to a very specific deobfuscation problem. And now I'm open for questions. Thank you very much. And I will publish the code after the workshop. So basically, I perhaps will add 1 or 2 more comments, and then I will upload the code and the samples and also the few slides that I had to the GitHub repository that is listed here. The question is, where's the sample from? Yes, it is the malware sample. It is, so basically, if we just Google it, it is the external malware family. So basically, this is from the APT group 128 that is viewed as a network proxy tool. So basically, they use it as a tooling when they are inside of a company to proxy the data in and out. Are there any other questions? then thank you very much. If you have any questions, you can ping me. I'm around in the Telegram channel. You can send me an email or Twitter. Basically, you have all the information you need here. And otherwise, thank you very much for having me, for your attention, for your interest, for your questions. And now Pancake can take over the session if he wants to. Thank you very much. There's one more question. If there's any particular reason why to use miasm for this kind of task? Well, yes and no. So basically, most of the things could have also be done the same way using a plain radare.
So, no more questions?
But the last time I checked radare in depth, there wasn't so much symbolic execution existing, such that with the symbolic execution part couldn't have been done like that, at least 2 months ago. So I don't know. I saw the talk yesterday that there is some basic functionality for symbolic execution now. Perhaps it might work now for on the ESIL level. I'm not sure about that, but at least a few months ago there wasn't any possibility. And yeah, miasm is one of the most stable.
Thank you, Tim. It was a great workshop. We'll go into the waiting scene for a while, and then we'll go for the last conference talks. Thank you.
There's one more question.
Oh, wait. There is another question.
The worst and most flexible binary analysis framework that I know that I use regularly. Okay, thank you very much. Okay, see you, bye, sir.
Welcome back to the conference. We'll continue with the next presentation from Sylvain, Karim, and Nicolas. You can start your talk.
Okay.
Thanks.
Thank you for joining the talk. So we'll speak now about how to simulate side channel with ESIL in Radar 2. Before starting, just a small presentation. So my name is Sylvain. I'm working at Security Evaluation Lab at Kudelski IoT, and my job is mainly doing hardware attacks, so with glitch, EM, and sometimes lasers. And I will let Karim and Nicolas introduce themselves.
I'm Karim Nicolas. I'm working with Sylvain Pelissier in the Security Evaluation Lab. My main duty is to basically assess the security of IoT embedded systems, and that's it.
And my name is Nicolas. I'm from the R&D department from Kudelski Security. I'm mostly working on embedded systems security research. So I do a lot of reverse engineering, protocol analysis, and so on.
So during our job, we found that fault attack is really interesting to defeat IoT devices, because usually you own the device, you have the device at home, so you can play with it, apply a fault attack on it. Usually this device is low cost. It has no protection or only software protection. So it's a really good target for that. And also setup to have a fault attack at home decreased a lot recently, for example, with the chip whisperer. So it's really interesting to start making fault on IoT devices. So just a quick recap on what is fault attacks. So the goal of a fault attack is to disturb the device execution from its normal behavior. So you have various hardware techniques to do that. I will just sum up them after. But recently, there was some research done to have fault attacks triggered by software or microarchitectural. This is the case for Rohammer, LVI, or Voltbone, which is as well a good, an interesting technique for fault attacks. So the cheapest solution to do fault is by voltage glitch. So you will lower the VCC during a short amount of time and then go back to the normal VCC level. And hopefully you will have the CPU which will behave differently, like maybe will skip an instruction or erase a register or so on. And here you can see one of our very low cost glitch setup, which does cost like less than $100. Then a bit more expensive but really efficient is EM fault attack. So here we see the chip shooter in action. Without modifying anything on the system on chip, you will apply electromagnetic pulse, and again it will change the behavior of the system on chip or the microcontroller. And finally, we have a laser fault attack. So here you will target a very specific region of the silicon with a laser pulse at a really precise timing. And then you will again fault some execution, some logic or some memories. And this setup is a bit expensive, but it's really, really efficient. So as I said before, effect on CPU can be really different. Depends the technique you've used for fault. And also it really depends when you attack. So it can be at the end, skipping instruction, corrupting register, corrupting memory, skipping read or write of the memory. So you have all kind of effect at the end. And since it's really, you have really a lot of different results, sometimes it can be interesting to simulate fault effect, because it's nice to have achieved a fault on your hardware, but then finding a way to use this fault in a good, to retry, for example, a private key or to access a non-authorized part of the code or so on, it's one step further. And you want first maybe to simulate this attack in software. In addition, for practical use case, you may not have access to the source code. It may be difficult to emulate the firmware you have because maybe there is no dev kit for the hardware you're evaluating, or maybe you don't know all the peripherals. And running hardware glitch or fault campaigns can be really long because you will have to test all the timing interval for all the positions, so it can be way too long. And as well, we found out that simulating fault can be interesting for code audit because maybe you want to catch some vulnerability you didn't find by hand, and it can show you some interesting property. And another interesting aspect we need to take care of is that we need to have to be able to simulate on on a lot of different architecture, because right now on IoT you have RISC-V, you have Xtensa, and so on. And for example, here, if we tried to open a RISC-V firmware in IDA, and we got an error because RISC-V is not natively supported by IDA. So this is an important property we wanted to simulate our fault attack. So we first searched for existing tool, and we found two of them. The first one is Lazart. It's developed at Grenoble. So this tool is based on LLVM, but you need source code to apply your fault. You first need the source, and then you apply the fault on the firmware. So it does not fit the need we had at the beginning. The second tool is FiSime. It's developed by a recurssion company. So the tool is based on Unicorn and Capstone. So you will need to stick to the architecture supported by Unicorn or Capstone. And the tool is not publicly available, so you will need to ask a license, to buy a license from recurssion. So we started to think about developing our own simulation tool. And we started to work with ESIL on Radar 2. And for that, I will let Nicolas introduce the tool.
Okay, so for those who don't know, ESIL is the intermediate language made to emulate or simulate specific instructions for various architectures. So our approach was to use Radar 2 ESIL to simulate several parts of the firmware. So the good thing is that even if you have a raw firmware, if you are doing the reverse engineering, you find some specific function that you want to fault, for instance, you can do everything from a single tool. So the idea was to instrument the ESIL virtual machine using R2pipe and Python, because it's way easier to program. So what we do is we can set up the stack and registers, then run the simulation and record the results. So for instance, the register at the end of a function. And when we do that, what we developed was a tool called the Glitchosaur 3000. It's a simple Python module where you can set the binary that you want to load, the start address for the simulation, its end address. You can set up the stack, the registers, and you can create a function that will basically tell whenever the fault you want to inject or the result is a success or not. Then the tool will run the simulation a lot of different time, injecting the faults at every step, at every instruction, then reset the VM, start again, etc. Collect all the results, then display them to the user. So as Sylvain said, there are a lot of different what we call fault model, which basically is the behavior of the CPU when a fault occurs. So we can implement a fault model directly using Python. So we created several fault models, several basic fault models. The first one is a simple instruction skip, which basically just skips one assembly instruction, then goes to the next one, and continues the simulation. Right now, the tool applies just one fault per simulation. So whenever you start a new simulation, it will set up the registers. Then, for instance, on the first cycle, we'll skip the first instruction, then continue the execution until the end of the function, give the results. On the next iteration, it will execute the first instruction, skip the second one, then continue the execution, etc., etc. So how does it look like in practice? So for instance, we take a simple password check function, which is right here. We can see that the developer is already quite aware about side channels because he's doing a loop that will always evaluate the 8 bytes of the password and not quit at the first one. So it's resilient to timing attacks. So what it will do is basically compare the two passwords that are here, XOR their results, and store them into this variable. So if the variable at the end is 0, then the two passwords are the same. If the value is different, then it will be a bad boy message. So when we run the tool, what it will do here is try to skip every instruction, every assembly instruction during the execution, and will display, whoop, sorry. Try to do it, to stop at the right time, there. So you will see that it found several ways to skip or to make the password checking function return a success by skipping all the compares and the jumps for the first 2 rounds of the loop. If you remember, the loop goes across all the bytes from the 2 passwords, and it will check if the counter is less than 7, then it will continue. If you look at the source code, the first 2 bytes are exactly the same. So if you let the loop run for at most 2 times, the result of the function will still be 0. So if we skip that specific jump here, it will then load the result into EAX, then return. That means that the function will return a 0. Then the program will think that the password was correct, which is exactly the behavior that we are looking for. So what we can do, we can tell the developer, okay, so you have a possible way to fault your IoT firmware in that specific case. So what he will do is, okay, so since with only 1 fault you can skip the password check, the developer will duplicate the password checking functions. So there will be 2 of them. So if you skip the for loop here, the second one will still see a discrepancy. Then the result will be different, and the function will say that the password is incorrect. Sounds good, right? Problem is that if you run the tool, it will tell you that you can still skip a jump instruction, which is right here. If we look at the assembly, you will see that what it will do is compare both results here, which is the equivalent of this specific if here, and it will skip that instruction. That means that if something goes wrong, it will set EAX to 1. That means the password is incorrect. But if you skip that instruction, it will then set the register to 0, which means password is correct, then return to the caller. That means that even this function, which looks way better protected, is still vulnerable because the branch will make the function try to return 1 first, but will return 0 in the end. So the best thing to do here is just to change the order of the returns. And in that case, even if you try to fault here, what it will do, it will return 1 instead of the 0. And this is the best way to prevent that specific function to be vulnerable to a fault attack on a device. So we were quite happy with the first results that we had, but we wanted to see if it was possible to, let's say, crank up the difficulty. So there are a lot of attacks available on AES, which means that if you are able to get the faulted result of an AES computation, if you have a certain amount of them, with the faults at the right places, you're able to recover the AES encryption key, even if you don't know the key previously. You just need to know one correct ciphertext and collect a lot of different faulted ciphertexts. So this is a bit more complex, but in the end, if it works, that means that our approach is good. So what we did was, okay, so we need to check if ESIL works correctly. So we took a tiny AES, which is a C implementation of AES, and we compiled it with an x86 compiler. Everything worked perfectly fine. But we tried to compile it on ARM and RISC-V, which are the targets that we see the most on IoT devices. And then we found that there was a lot of different problems. There were infinite loops, wrong calculations, and this kind of stuff. So that means that there's a problem with ESIL during our tests. So before trying to make AES work correctly, we first needed to correct ESIL.
So as explained before, we wanted to find a way to make the Balda test work on new architecture that was not working at the moment. So we noticed that if we start to figure out what was wrong in ESIL, we could first improve it, but also we can probably validate what happens in ESIL against a real device just to know if ESIL was behaving properly. So here the goal was to develop a tool to automate this process and to do it for few instructions or functions, as well as full binary execution. r2 allows to, let's say, abstract the architecture you are using as soon as the ESIL works well. For that, we instrumented r2 with Python and R2pipe to do this comparison process in an automated fashion. What the tool does basically is opening two pipes, one for the debug. Let's say it can be a QEMU or a real device through GTAG, SWD, or even a GDB session on the host. And in the second pipe, we will open just an ESIL, set up the VM, and synchronize the ESIL VM with the debug. So this means that registers and memory space has to be the same. And then we step and compare until discrepancy happens. So the use case, as said before, is either compiled binary. So for IoT system, it's quite convenient if you can just put your firmware, load it properly, and execute the whole firmware and see where it blows, basically. Of course, for peripherals, it will probably not work, but this is where the tool will help you a bit, because as you can synchronize the register between the tool, between the debug and ESIL pipe, then you will be able to recover yourself. I've been able to use it for unit testings. Let's say if you wanted to test specific instruction, like the r2r tool does. So basically what you can do is set up your favorite IoT device through SWD, and you connect, for instance, with OpenOCD and GDB, and then you can simply relocate the current map to an executable memory space, write the assembly there, and point the instruction pointer to that, and execute the test, and compare basically the results you get in the registers. So here I just explain a bit what the tool does. So basically, it allows to display what was the previous instruction that you executed and the current one, highlight differences between registers, synchronize the registers between the debug and ESIL pipe, and interact with both pipes at the same time or one pipe at a time after each step. So we'll go through a quick demo just to see how the tool works. So here you can see I colorized a bit the output. So in green you have the ESIL information. In red, you have the debug information. I call it debug, but it's basically the QEMU pipe or real device pipe. We can call it like this. And the differences will be highlighted in red here in the shell, so you can easily spot the differences between the registers. So I go full screen. Here the tool is launched. Here it's copying the stack memory because it runs in QEMU. Here we can see already that I didn't synchronize by default the register, so I will go ahead and do it. So I synchronize the debug register with the ESIL pipe. And then we see at some point we have a discrepancy, so the execution stops. So as here for instance, I resynchronize the ESIL pipe. Then I wanted to interact with the pipe, so I just put E, and then I display, for instance, register states. Then I can just quit this, let's say, interactive commands, come back, display a register if you want, and continue execution. Here we can see also it will happen many differences on the code. So I will print some of the memory space on both pipes at the same time. And here you can see the differences if there are any. It won't be highlighted, however, but you will see it probably by just seeing the outputs. So these tools allowed us to patch multiple things in ESIL. Basically, we have still one PR in progress for fixing the IT block, but we have already 7 pull requests merged into Radar2. Most of them are for RISC-V fix or ARM fix. Also, we fix multiple issues opened by other users. And now we've tested this on ARM. It works fine for thumb mode and RISC-V also.
So once we were able to make a tiny AES work on ESIL, we are able to get back to our initial tests that we wanted to do, which was trying to fault AES and recover the private key by looking only at the faulted ciphertexts. So if we take the tool that we created before, I will run the video, which will show, you will see on the left which instruction during AES computation has been skipped. And on the right here, you will see the faulted AES results. And if I click pause at the right time, it will display the AES key. So you will see that at the beginning, the ciphertext look quite gibberish, so you don't see a lot of differences. But the deeper we are within the AES computation, you will see that only some specific bytes will start to change, and the others will stay the same, like right here. Just to explain also this simulation, since I was synchronizing the threads and it took a lot of time to get the result displayed at the same time, the total simulation takes about 1 hour. Here, if we are using the threads correctly, it takes about 15 to 20 minutes. I will try to, too late. If I just write here, okay. Sorry for the video, but you will see that in the end, it will take all the ciphertexts that are here, apply a specific AES, a specific attack on AES, and it will be able to recover the main key, which is the one that is set in the example of tiny AES. So that means that our attack worked. So we were quite happy with that. And we're able also to play with different other variations. So everything looks quite fine to us. In the future work, what we want to do is to implement multiple faults during the same simulation, because this is something that we are able to do on real targets. That means that creating one fault at a specific time, then another one during the same execution. It's way more difficult and way more precise to do, but this is something that is doable. Also, we want to add new fault models. For instance, Sylvain talked about the laser fault attacks. The thing is that with laser faults, you are able to flip just one specific bit of an instruction or a memory read. That means that maybe you can just mutate one specific instruction to be something else, and this will produce maybe more interesting results. Also, our goal is to also enhance ESIL for maybe other architectures, or to add new features to existing ones, for instance, ARM, which we are still doing.
So to sum up this presentation, we have made a tool to simulate fault, and we figure out that it worked well because we were able to reproduce then the attack on real hardware. We are able as well to identify potential fault injection during code audit, just with the compiled code. So the tool the two tools we've presented during this conference will be open source just right now after the conference. So you will be able to start to play with them, and there will be firmware example as well, so you could reproduce the attack which we have been presented just right now. And to sum up, this really interesting because as soon as you have an architecture which is supported by ESIL, by Radar 2, then you can start to play and to inject fault. Anyway, ESIL has to be properly implemented, which is not always the case. So you may have some work to do, but hopefully at the end you will have something working, and you will be able to simulate fault on this architecture. So it's really interesting to work with that. I think we still have some time. We have a small bonus. So we speak about fault, in fact, but it's also possible to have a side channel, to simulate side channel in a way, because we have, for example, AES, and we have all the information for read and write during the execution. So we can generate easily a trace with all the memory access during AES execution. And then we can apply a kind of CPA, which is a more differential computational analysis on these traces, and then we'll be able to recover the key. So the tool to do that already exists. It's in the side channel Marvels in GitHub, and with ESIL we can create these traces. We have here a single trace of an AES execution. So we clearly see the 10 rounds of AES, and so the first part is the key schedule. So with all the key loaded in memory, and then we clearly distinguish the 10 rounds of AES. So with this kind of trace, we can then apply CPA and recover the AES key, which is as well really, really interesting. So I think that's all for us. We would like really to thank the organizer again. It was really, really nicely organized. And if you have any question, feel free to ask now or ping us on Twitter or Telegram. We'll be there to answer. Thank you very much.
Thank you.
Thank you.
Cool, thank you. I don't know if there are any questions.
There's one here, but I think we already answered this one.
Yep.
The video will be available for someone to watch later on. And that is the only question we have right now.
Okay, so any other question, you will be able to find the speakers in the Telegram channels. Otherwise, you'll have the Twitter handles here. So anyway, amazing presentation. Thanks for all your work and thanks for attending. So yeah, I mean, there is only one more talk left. I will jump into the waiting scene and we'll start the next presentation. Thank you.
Thank you.
Thank you.
So we have the last presentation for today. This is Jan Seredynski, and he will be speaking about the security review of 1,300 AppStore applications. He's a mobile security engineer working at Square. And well, let's see what he has to show for us. After this we'll be playing some more music, and we'll be close the stream until tomorrow. So thanks for watching. It's all in Jan's hand.
Yep. Thank you, Pancake, for a great introduction. So, hello, my name is Jan Seredynski, and I will talk about my project where I combined Radar 2 and Frida to check how many apps in App Store use runtime application self-protection. So I tested over 1,300 apps for jailbreak, debugger, and tampering detection, and I would love to share with you some results and some interesting insights. Also, when I started this project, I had no knowledge about Radar 2, and over a few months, I actually built a framework based on it. So if you are not sure about starting your adventure with R2, I hope that this presentation will encourage you to give it a try. But firstly, let's clarify what Rust is and why it's good to use it in our apps. I will start with an example, and let's say that we work for a bank or a big organization, and a hacker compromises our customer's phone and extracts their private data from our app. And that will definitely lead to reputation loss and probably some theft. And Rust is a set of techniques that helps us protecting our apps against such attacks. While it's not an easy task for a hacker to compromise our phone, there are ready solutions on the black market that hackers can buy and use against us or our customers. And here you can see a price table from a bounty program of Zerodium. But I believe that those prices are very similar to prices on the black market. And the prices start from $100,000 for a local privilege escalation. And for example, that means that a victim can install a malicious app from the App Store, and this app will compromise his device. For $200,000, someone can prepare a malicious website that will compromise our phone when we open it in our browser. And for $500,000, someone can buy a payload that will compromise the system via popular messaging app, like, for example, WhatsApp, Telegram, or Messenger, for example. Prices are huge, but if a hacker targets a big number of people or someone extremely rich, it may pay off, which was the case for Jeff Bezos, who was actually hacked with WhatsApp in 2018. So what happens after the phone gets compromised? For example, a malicious website in Safari can escape the sandbox and escalate local privileges. Then it can scan our banking app container and look for preferences, databases, some media, cached HTTP responses, and cookies, and search for temporary files. And in all of those places, they can find some sensitive private data. However, hopefully the sensitive data is encrypted and placed inside the keychain, which raises the bar significantly for static analysis. In that case, the attacker can still target our app via dynamic execution. And for example, they can install mobile substrate on the system and use it to attack an app in the runtime. And that's when runtime application self-protection comes in handy, because it can prevent runtime attacks. So we talked a lot about runtime application self-protection, but how exactly does it work? So it mostly checks for jailbroken system, attached debugger, Frida, or if an app was patched. And for example, a jailbroken system leaves some file artifacts in the file system. And one of Rust techniques is to look for those files. And for example, it can look for Cydia or mobile substrate library. And also some files may have different permissions than usual, or some files can be just replaced by soft links and moved to a different location. Also, on a jailbroken phone, the sandbox can be corrupted. So normally the sandbox should protect against accessing resources outside of the sandbox. So Rust can try to access those forbidden resources, and if it succeeds, it means that the system is compromised. And for example, it can run some functions like fork or exit or open. And also it can try to use some features that are not enlisted in the entitlements. And if it works, it means that the sandbox is probably corrupted. Another Rust technique is to check for file system permissions. And for example, the default permission for the root file system is that it is read-only. And on a jailbroken device, it's not the case because it's also writable. Rust also checks for a debugger. It checks if it's attached, and it uses ptrace with pt deny attached option to check for it, or it can use sysctl, or it can use get parent PID. And if an app is spawned by a debugger, the result of that function will not be equal to 1. Also, Rust can check if an app is instrumented by Frida or mobile substrate, or just a part of the code is modified. It can use, for example, the dynamic linker inspection to find some attached suspicious modules, or it can check for trampolines or run checksums on the text segment. So now when we know what Rust is and why we need it, we can ask a question: how many apps in the App Store use runtime application self-protection? And actually, this question motivated me to start this project. And I decided to start with baby steps. And firstly, I created a framework to detect Rust techniques in just a single app. I split the framework into 2 parts, the static analysis and dynamic analysis part. The static analysis obviously uses Radar 2 under the hood with Python bindings, and it searches for strings, for example, /bin/bash or Cydia or mobile substrate or Frida. It also checks for suspicious imports, like, for example, fork, ptrace, or lstat. It also looks for system calls along with corresponding syscall IDs. However, R2 has a nice feature that recognizes system calls, so I didn't have to code it myself. And I also enumerated frameworks to check if an app uses, for example, SSL pinning. So for example, if an app uses TrustKit framework on iOS, I could assume that the app has SSL pinning inside. In my approach, I spawned an app and ran it for 10 seconds and kept it on a screen without any further GUI exploration. So the dynamic analysis would not detect any Rust protection after the login screen. But static analysis does. So that's why I actually combined those 2 methods. So the other method, the dynamic analysis part, is done with Frida. And I realized that it's pointless to hook all Objective-C and Swift function in the app because the iOS API is too huge and there are too many places to hook. So I needed to find a sink where all iOS API calls end up. And I came up with an idea that Swift API may call libc directly or via Objective-C because of some legacy. And Objective-C will then call libc, which eventually call libsystem, where all the system calls instructions are. So the libsystem library sounds like a great place to actually put our hooks. And I hooked exactly there, which saved me a lot of time on hooking all of Swift and Objective-C API functions. Like, for example, does the file exist? Well, obviously, that function doesn't exist in iOS world, but it's just like a dummy example that I would have to hook all of similar functions. It has also another advantage. I mean, the dynamic analysis has another advantage because some Rasp solutions only calculate checksums on the binary. So hooking libc or kernel lib doesn't fire up any Rasp alarms. Well, so here I mean that if we actually hook the lib system library, many Rasp solutions just don't checksum it. So we can just hook there and it won't fire up any alarm. So at this point, I knew how to scan one app, but now I had to focus on automating the whole process to test thousands of apps in AppStore. And it turned out to be even a bigger challenge than the previous task. And as you may imagine, Apple doesn't really help with parsing the App Store. And here I'm really curious about your ideas. How do you actually automate downloading and installing apps? And feel free to add your ideas to Q&A section. Later on, we can talk about them. But for now, I'll show you the approach that I actually used and with which I ended up. Well, so I started with searching for a ready solution, and I found one really, really awesome project, which is called the iOS. But I checked on the GitHub, and the last commit that I saw in the repo was actually in 2015 when iOS 8 was around. But anyway, I gave it a try, and it looked really great and promising. It had an easy scheduler and really, really clean code. And it had really many awesome features. Like it could, for example, queue apps on many phones that could speed up the whole process significantly. I also like it for its simplicity because it runs an HTTP server as a twig inside the Springboard to communicate with the scheduler. And also it uses Springboard private API to download an app from the App Store. So I actually had a hint where to start looking from, where to start my research. And everything looked great, but it turned out that this solution worked only until iOS 10 because Apple added a additional new step to confirm an installation. And on the next screen, you will see that magic window. So here you can see that new extra window that was introduced in iOS 11. And actually, all we need to do is to write a tweak to press that install button for us for every application. So whenever we install an app with the private API, that magic window pops up, and we just need to write a tweak to just click for us install button. And since we start downloading an app from the Springboard, I spent many days on reverse engineering the Springboard itself and looked for this install button. And I couldn't find it at all. I really spent a lot, many days on it. And one day I came up with an idea to list all processes that were running at this moment on the system. And I found a solution. I found that the new window doesn't come from the Springboard. It actually comes from the Passbook app and is displayed as a remote view on a Springboard. And well, knowing that, I added my tweak to Passbook to always click on the install button when it appears. And so the new updated flow look like this on the left side here. So firstly, the dispatcher connects to the HTTP server. That is a twig inside the Springboard. Actually, all red boxes are twigs. Then the HTTP server calls a private API that starts downloading the app. And the private API is called stored purchase, and we just need to pass a bundle ID to it, so it's quite easy. And then when we call that API, the iOS pops up that magic window from Passbook, but we already have it tweaked, so the install button gets actually clicked for us. And at this point, the app is being downloaded and installed. Later on, the dispatcher runs the scanner, so that is another part of the framework, and the scanner uses Frida client to check if the app is already installed. Yeah, because obviously it needs a few seconds to get downloaded and installed. And when it's installed, it spawns it and decrypts it, and later on dumps it to the desktop. Then the dispatcher runs static analysis with Radar 2. And after it spawns the app again with Frida and hook in all relevant places. And after 10 seconds, it closes the app. And now time for some results. So I set up the framework to download 100 the most popular apps from 13 different categories. And the AppStore actually provides a really nice API to list apps by popularity. So it was a bit easier for me to actually categorize it. And I started the framework and ran it continuously for 2 days. And on average, it took 2 minutes to download an app, scan it with Radar 2, and run Frida for 10 seconds. And when I finished it, I was a bit shocked that so many apps actually use Rasp. But let's keep in mind that these apps are top 100 apps for each category, and don't expect the whole App Store to be like that. Those are just top apps. In this chart, you can see the percentage of apps with Rasp protection that checked for file artifacts. The blue bar relates to strings found with static analysis. The orange bar relates to strings found with the dynamic analysis. And here we can see that not all of apps executed Rasp protection. So probably some of them are executed after the login screen, because we don't really use the GUI exploration feature here. Okay, also the green bar relates to strings that were found during dynamic analysis, but are not in the clear text in the binary. So they were encrypted in the binary and decrypted in the runtime. So you can see actually how many apps encrypts firstly strings and then decrypts them in the runtime to make it harder for potential attackers. And well, checking for file artifacts is the easiest way to detect a jailbroken system, at least in my view. So this chart shows more or less the real proportion of apps using at least one Rasp protection. And we can easily spot that games use significantly more Rasp than other industries, even more than finance. That was a bit shocking for me. But we can see that overall about 60% of apps have at least one kind of protection. Another two Rasp techniques are checking for corrupted sandbox and debugger detection. And a half of the sandbox is often tested with forbidden functions like fork, kill, or popen. However, invoking this function may lead to undefined behavior. So we can see that this technique isn't really used quite often in the runtime nowadays, as compared to checking for file artifacts or debugger detection or instrumentation detection, which I will cover in the next slide. A really great insight from those graphs is that if an app has a debugger detection at all, it almost always uses it at the startup phase. And here we can see again that games, books, and education have significantly more apps that protect themselves in runtime. And here I found those two Rust techniques to be the most advanced and effective. The instrumentation detection chart shows the proportion of apps that use those three functions below and can be used for detecting an injected module or getting an address of a function to perform a checksum. The system call chart shows the proportion of apps with hard-coded system call instructions. And below the chart, I listed the most popular system calls that I found in the apps ordered by their popularity. And we can see that system calls are mostly used for checking for a debugger. And an interesting insight here is that many apps use system calls for working with network sockets. And I didn't dive into it, but I believe that they are not used for jailbreak detection, but rather for a custom secure networking module that keeps checking for the checksum. And using this approach hinders an attacker because he would need to hook the application's binary instead of libc. So it would be easier for a Rust guard to detect it. And to sum up, about 60% of apps have at least one kind of Rust protection. But again, don't expect the whole App Store to be like that. I just tested the most popular apps for each category. And now we can come up with a question whether companies protect us or themselves. And if we compare games and entertainment apps with finance and medical apps, we can see a huge gap in Rust usage. Games and entertainment apps use Rust more frequently and use more advanced techniques. And this is reasonable for games vendors because they need to protect against cheating or IP laws. And the same applies to entertainment apps like Netflix, for example. They just need to protect their content. I think that it shows that companies are more likely to use Rust if they protect themselves rather than their customers. At least that research indicates it. And well, many apps use Rust protection after the login screen, but is it really a good idea? So, for example, if the phone is compromised, the attacker could put a keylogger and get our password at the login screen or the sign-up screen. And well, anyway, the app may block access to its online system, but the credentials are already compromised. And if I use the same credentials for other websites, then they are just leaked and compromised. So I think it's just better to inform the customer ahead. And the bank app gives really nice example here. So on the left side, we can see a screen of a banking application that alerts a user about detected jailbreak just after the startup of the application. And honestly, I'd prefer an app to inform me like this instead of performing checks after the login screen, after I already type in my credentials. And that would be it. Thank you for your attention. I'll move to the Q&A section right now. And well, so first question that I will just try to find a good question here. So does your data consider obfuscated applications? Can we check obfuscated applications with such approach, how it applies to your data? So obfuscated application still need to use some functions to check for example, compromise sandbox. For example, it uses fork or exit, and they actually need to use it from libc, or if not libc, they would have to use system calls. And once you see system calls hard-coded in the binary, you could assume that there is some kind of Rust protection. I hope it answers that question. Well, also obfuscated apps, and well, that's why I also use dynamic analysis. So I would reveal some obfuscated values, like for example, the encrypted strings that we saw on the first chart. I wouldn't be able to actually find them with static analysis, and that was only possible due to dynamic one. Okay, another question. So, have you found many apps that detect hooks in the system libs? Actually, I didn't dive that deep into it. I think that would be really hard to actually automate it. Yeah, that would definitely be harder to automate it. My approach, well, the idea of my project was more about like researching the current state of the market and seeing just how many apps use Rust, not how advanced that Rust is. Well, obviously, I categorized Rust protections into instrumentation detection, debugger detection, and so on. But checking for hooks in the system libs would be a bit harder, I believe. Let me move to another question. Well, firstly, do we still have time? I see that we have still
go
a couple
ahead.
of minutes. Okay, that is a really nice question. What are disadvantages of your analysis model? What vulnerabilities scenarios might miss? So, well, actually, a few things could have gone wrong, but I actually did my best to fix it. So firstly, there are many libraries, like additional frameworks. I don't remember correctly, but I think that one was from Google, and it was something like analytics framework, and it had some kind of jailbreak detection, and many apps actually used it, but they didn't do anything with it. And there are just many frameworks that checks for the data, but don't really leverage it in any way. So I just collected the fingerprints of those framework, and I just removed them from my results. And disadvantages of analysis model. So also, well, some protections may be revealed after another in a sequential way. So, for example, if the first protection in a protected app is really advanced, then my research wouldn't find it. But if it starts with debugger detection, instrumentation detection, or others that I covered, it will be revealed. But as I said before, I just focused on maybe not easy protections, but like reasonable just reasonable, not that advanced that I would have to spend years on creating the model actually. So those are two possible disadvantages here in my model. And maybe the last question. So any idea as to why Cydia apps seems to be checked more often? I would expect general check to be more popular since not all jailbreaks use Cydia. Well, I have no idea why Rasp solutions check for Cydia, and well, what I believe is that many apps don't buy actually ready Rust products, and the developers just try to use anything what they find on the internet. And I can bet that if you search on Google how to detect a jailbreak on your phone, the first answer will be to check for Cydia app. And yeah, I hope that answer the question. And also that's why it was easier for me to actually find those apps, because they use like quite easy protections as compared to advanced Rasp solutions. And yeah, I think I'm already I'm already beyond the allocated slot. So thank you for having me here. Thank you for organizing that awesome conference. And back to you, Pancake.
Thank you, Jan. It was an amazing presentation. Thanks for having us in the conference. So yeah, it was amazing to see your work. We will close the conference for today. So we'll see. We'll expect you to join the stream tomorrow at the same time, 5 p.m. So thanks for watching us, and see you tomorrow.